Okay, so what if a mathematical impossibility, a rule that's been set in stone for over 200 years, just got smashed to pieces? That's what we're digging into today. We're looking at a pretty bold claim, a solution to a problem that generations of mathematicians were taught could never be solved. You know, in the world of mathematics, there are some rules you just don't question. They're seen as absolute boundaries. They define the very limits of what we can know and what we can solve. And for the last couple of centuries, one of those hard and fast boundaries was all about solving these really, really complex polynomial equations. But then you get a statement like this. And this right here is at the absolute heart of our explainer. It's a direct challenge to a foundational piece of algebra. It's basically saying that what everyone thought was a dead end was maybe just a temporary roadblock. All right, so to really get why this is such a big deal, we got to go back a bit. We need to understand this so-called unbroken wall that's been standing in the middle of algebra for centuries. And here it is. This is the wall. It's called the Abel-Ruffini theorem. Now, in simple terms, what it says is that there's no general catch-all formula, kind of like that quadratic formula you probably remember from school, to find the exact answers for equations once they get to the fifth degree or higher. For mathematicians, this wasn't just, oh, this is a tough problem. No, it was considered a fundamental dead end. It was like the map of algebra just stopped. And look, this wasn't just some fleeting idea. It was cemented way back in 1824 by Niels Henrik Abel. Then, the brilliant heuristic law came along and explained why it was impossible. So for the next 200-plus years, this wasn't just a theory. It was an accepted fundamental truth. And the impact of that? It was huge. It meant that mathematicians, physicists, engineers, pretty much everyone had to just settle for close enough. Instead of getting perfect, exact answers, they had to rely on approximations. The source material we're looking at even calls it a kind of philosophical fatalism that totally shaped entire fields of research for centuries. Which, of course, brings us right back to today. Because after 2 whole centuries of accepting this limit, someone is now claiming they've smashed right through that wall. And that someone is Professor Mourad Sultan Ezouidi, the author of the work we're examining. He's put forward a totally new theorem, and he claims it does what everyone thought was impossible, finding those precise, exact, symbolic solutions for these high-degree equations. And this quote, this really tells you everything you need to know about the mindset here. It's a flat-out refusal to accept a boundary that's been there forever. It's all about trying to find a path that, for 200 years, the entire world of mathematics believed just didn't exist. So, okay, what's the new secret sauce here? Well, it's called Ezoudi's theorem. The idea is, instead of trying to brute force a solution with the old tools, this method uses this really clever framework of recursive steps. You can almost think of it like a set of instructions that lets the messy equation sort of untangle itself, step by step, until, bam, it reveals its own exact answers. So, how does this new way of thinking really stack up against 200 years of classical math? Let's put them side by side and see. Right off the bat, just on a philosophical level, the difference is, well, it's stark. The classic approach basically said, okay, there's a limit, we accept it, we'll just use approximations. But Ezoudi's approach, as the source describes it, completely rejects that fatalism. It's all about chasing down those perfect, algebraically verifiable answers. And this chart really breaks it down for us. You can see, where the classical methods just hit a brick wall and said impossible, Ezoudi's theorem claims it can deliver exact, symbolic solutions. It's a huge shift, right? Moving away from the old theories toward these new, recursive discriminant structures. Basically, it's the difference between good enough and what's claimed to be 100% algebraically perfect. So, here's the really crucial point, the core of the new argument. It's all about reinterpreting history. The claim is that Abel didn't prove it was absolutely impossible forever and ever. He just proved it was impossible with the mathematical tools they had back then. See the difference? The theorem wasn't a limit on algebra itself, just a limit on a specific way of doing things. Okay, so that's the theory, but does it actually work? Let's take a look. We're going to walk through a real, concrete example from the source material. All right, here's the test. A 9th-degree polynomial. I mean, just look at it. It's intimidating, right? And for good reason. According to 200 years of math, finding a nice, clean, exact answer for this is supposed to be impossible. You're supposed to end up with some long, messy decimal approximation, not a perfect solution. Now, the source lays out a pretty clear 4-step process. We're not going to get lost in the weeds with all the formulas, but the gist is this. The method takes the equation's basic ingredients, its coefficients, and runs them through this series of special steps and transformations. The whole point is to just systematically break the problem down until the exact answers just pop out.
And after all that, what's the answer? What's the exact solution to that monster equation? It's the number 1. That's it. According to the author, the exact root is just 1, with a multiplicity of 9. A perfectly clean, simple, symbolic answer to a problem that was supposed to be unsolvable. So, let's just imagine for a second that this holds up, that it survives all the scrutiny from the global math community. What would that mean? What are the implications? What does this actually change? Well, according to the source, the consequences could be absolutely profound. We're talking about redefining the very meaning of solvability in algebra. All of a sudden, no polynomial, no matter how ridiculously high its degree, would be off limits. It would literally turn a historical impossibility into a modern-day discovery. And really, that's the ultimate takeaway here. This claim isn't just about solving one tricky equation. It's about changing the fundamental rules of the game. It's about pushing the boundaries of what we even thought was possible in math. Which leaves us with one last pretty big question to think about. The source material frames this as nothing short of a revolution. And if a mathematical law that's been accepted as fact for over 200 years can be challenged like this, it really makes you wonder, right? What other impossibilities out there are just waiting for somebody, somewhere, to come along and look at them in a completely new way?